Welcome to the ZTF Summer School 2022. This is year 2 of a 3-year effort. Many of you, I don't know exactly the fraction, but it's not a small fraction, were here last year. And so the concept of the summer school, or the ZTF summer school series, it's a 3-year series. So last year we did variable stars. This year we're doing multi-messenger astronomy, and then next year we're doing transients. Now, the truth is we're using kind of science topics as a way of getting at technical acumen here, right? So we're going to introduce you to ZTF, we're going to introduce you to multi-messenger astronomy, but in broad strokes, we're looking to teach you things about Bayesian inference, machine learning, some time series stuff. We'll talk about how to get access to alert stream, how to get access to light curves. We'll talk about, since we're doing multi-messenger astronomy, we'll talk about doing, gravitational wave observing scenarios and some other things. And so this means a couple of things. So for those of you who were here last year, some things will inevitably be very similar, right? Day 1, where we're doing things like light curve access or alert streams, is going to be the same, right? There's just no way around it. And so we appreciate in advance your patience and, to some extent, your support of others as we deal with the inevitable technical and learning things issues that will come with a school like this, right? So for those of you who already do this, let's say, some of this stuff for a living, don't be afraid to help each other out, right? And so the students vastly outnumber the TAs here, right? We have 7 or 8 speakers lined up. We'll have kind of a similar number of TAs of sorts who are active on Slack. Some are in this room, some are elsewhere. But because there's something like 100 and some students signed up for this thing, and we got 60 online, and a bunch of you in the room here, like, there's no way that we will be able to do this without folks working together in groups, being active, all that kind of stuff, right? The next thing I will say about this school is it's not, because it's hybrid, it faces all of the challenges of a school of this kind. Schools that are in person, right? You can run them from 9 to 5. You can, have morning and afternoon sessions. You can sort of have everything be synchronous. That just can't be how it works here, right? We have, 15, 20 in the room here, but many of our attendees are from around the world. Welcome to all of you from around the world here, from Minnesota. And so the way that this is going to work is, we'll be running this synchronous session from, something like 9 to 12:30 each day. And so the way that we have it planned is, there'll be a couple of science talks per day, which will take kind of the first half-ish of the session, maybe more. And then we'll be introducing what are meant to be the hands-on tutorials in the form of Jupyter notebooks that are meant to either be like, introduce you to, in this case today, how to get the alert stream and that kind of thing, as well as kind of homeworks of sorts, which are designed to apply those skills in some way. Now, again, this is inevitably going to need to be kind of flexible, right? Because, again, some people will, it's the middle of night for some people. And so the asynchronous part of the session, there's folks in the room here who will hopefully be here all afternoon, kind of working with us as we go through the things. But there will be folks online who, go to bed as soon as this is done and then wake up in the morning and, hopefully are active on Slack together, right? And so again, we will appreciate in advance your, in some sense, generosity when it comes to, you know, understanding the flexibility that running a school like this requires. So the plan is we'll run this each day this week. We'll aim to be around till something like 5 in the room. So we'll run until 12:30. We'll order lunch. We'll have lunch. Come back for a handful of hours in the afternoon. Work together, that kind of stuff. Except on Friday, where we'll probably cut out early because a bunch of people have flights and all that stuff. Right. So we'll I don't know. I think the core staff will be here till late afternoon on Friday, but we understand people will be out. Right. So the school runs around GitHub, around this ZTF summer school GitHub that we have. And so the kind of course of action is, so this morning I uploaded the first lecture. And so hopefully you all can see that when you git clone or git pull your environment. And again, some of you will be running these locally. You'll build some kind of conda environment. Maybe you'll use the YAML file that we've provided. Maybe you won't. You'll just pip install some stuff. You'll work together to do that. That's all fine. Some of you will be working on Colab. Again, there's this huge variety of skill sets that exist when it comes to interacting with the technical software side. And so do post in tech support. Even if you're local here, consider also posting in Slack, right? Because the same questions that are asked, the same questions that are asked by you here are inevitably the same questions that need to be answered online. So as much as possible, we want to be using Slack as a way to at least make a history of what's happening, right? Because otherwise, again, there's just not enough people to help everyone solve every technical issue ever, but hopefully we can, group think it and we'll be successful that way. Right, so for those of you who are in person, we'll have coffee and some snacks here in the morning. We'll order lunch, and then we'll also have some snacks in the afternoon. So hopefully that incentivizes people to stay for a while. Okay, so I think I'd like us, we won't be able to do everyone because we just don't have time for it. But could the TAs wave their hands, say who they're, well, actually I'll start, right? So I'm Michael. I'm a professor here at Minnesota. I'm from Minnesota, he, him pronouns. And my favorite activity on campus of all is to walk around and talk to the squirrels. That's my favorite thing to do. Yeah. Andrew, could you say hi?
Hi, I'm Andrew, I'm a third-year graduate student working with Michael. Hi everyone, I'm Avery. I work at IPAC at Southwest. I'm here in the ZTF releases.
Avery knows more than any of us on everything ZTF. So don't ask me questions. That's them questions, right? Yeah. So if you could, folks, post on Slack, who you are, where you're from. So one of the challenges we had last year. So last year, some of you know, we ran the school completely online. We attempted to make groups that would go into breakout rooms and sort of work together in kind of an imposed environment that way. A lot of pushback, I would say, from that. There was, I think there's inevitably a challenge to create sort of, cohesive groups in a short week, much less those that are, online here. However, so we're moving away from that because, again, there were certain challenges. However, the work that we're doing is designed to work with others, right? And so for example, for those in the room, we will be asking you And I expect you'll have maybe a bit of an easier time because some things are just a little easier in person. But do work together, struggle through problems, especially before, necessarily talking to the TAs, just because, this is part of how science works. Right. Anything else? Yeah. Oh yeah. We do. So we have a dedicated channel for each day. So a lot of you are using Slack already, tech support, school 2022, general, some talking about the same topics in each. So maybe do some cross-checking. If you can, do consider using day 1, 2, 3, 4, 5, join those channels as those go on, so that we can try to keep the conversations about, for example, like, the notebook for the alert stream access or whatever contained to the day 1. Again, so folks who will probably come back to this, tomorrow morning, their time or something, can try to track the conversations, because let's say, not everyone is going to be doing this school from 9 to 5 Central Time, is my point. So do consider engaging there to make this as, work for everyone, let's say it like that. And the other thing is, do ask for help, right? There's an incredible range of expertise in this room and online, right? Some of the quote unquote students, right, participants in the summer school, know more about many of these topics than I do. Some prepared the data sets that we're going to use, right? And so there's plenty of participants who kind of are participating some days and are actually the experts other days. And so again, I think this is a huge advantage. Don't be afraid to ask, quote unquote, dumb questions. And don't be afraid to listen to the other participants, because again, a lot of the people who are here are working in kind of various aspects of this multi-messenger astronomy thing, right? I think this topic, even relative to, for example, various variable stars or just transients in general, really inevitably means that different people are going to have those expertise, right? So if I wear my LIGO hat, I'm a gravitational wave person. If I wear my ZTF hat, I'm an optical person. But again, you'll hear talks from, let's say true gravitational wave people, or, people who do, only fast transient science with ZTF. Again, these are all speakers, but once you walk away from those topics, especially once you change messenger or something, we don't know anything, right? And so again, there's no shame in asking lots of questions. And again, we want you to have fun. There's no stress. There's no grade, right? We will, for those who need it, we will give you your form that says, good job, you completed the school. We're not going to be looking at, we're not going to be looking at your notebooks. There's no like sign out. There's no anything for that. The vast majority of you are graduate students, right? So we expect that you, behave like graduate students. You're here because you want to be, et cetera, et cetera. Yeah, so there's none of that going on. There's no, you have to get Andrew's permission to like leave for the day. If you got telecons all afternoon, as many of you probably do for your various things, that's okay, right? So you just make work what you can. Okay, so the plan, subject to change, right? So day 1, so I will spend, a couple of minutes introducing ZTF in the school as of now. You're going to hear from Shreya Anand, who's a Caltech graduate student, who's going to talk about LIGO and gravitational wave follow-up stuff. And then together we'll be talking in the remaining time about how to get access to alert stream data and Bayesian inference, and basically introduce the notebooks you'll do today. Tomorrow, we're going to be doing some focus sessions on, fast transient science with ZTF, as well as how to interact with various gravitational wave data products and observing scenarios. Now, again, this is challenging in the sense of, in this one summer school, which is called ZTF, which kind of says optical data, because it's multi-messenger stuff, we're going to be doing some optical astronomy, we're going to be doing some gravitational wave astronomy, we're going to be doing some other things. And so, yeah, we're going to have to be a little flexible on our feet here. Day 3, Tomas Ahumada, who's defending his PhD on Thursday, will be talking about the way we do gamma ray burst follow-up from within ZTF. And then Robert Stein, who leads the neutrino follow-up effort. And so Robert's preparing a sort of, let's say, focus session on, you know, in some sense, how neutrino follow-up's different than doing, let's say, gravitational wave follow-up in the optical. And then we'll also be introducing how to do some compact binary light curve modeling with Kilinovi. So that, I would say, kind of day 1 through 3 broadly is Bayesian statistics, some gravitational wave stuff. You know, if I have a light curve, what do I do with it? How do I extract science? That kind of thing. Day 4 and 5, we transition more into the machine learning stuff. So Ari Shravan, who's currently a postdoc at Caltech and soon to be faculty member at Drexel, she's going to be introducing, machine learning in the context of multi-messenger astronomy. Guy Meir, who does kind of a lot of the big data processing for ZTF in the context of Sky Portal and other things, will be talking about how to basically interact with these large data sets, apply some machine learning to them, that kind of thing. And we'll be taking a look at the simulated sample of potential gravitational wave and fast transients that Ari has been putting together over the last 6 months, and we'll do a focus session on that. Day 5, Julian Peloton, who's he's a research scientist at AGC Lab over in Orsay. He's one of the PIs of the Think broker. He'll be talking about brokers. Yashvi Sharma, who's a graduate student at Caltech, will be talking about spectroscopic classification. And yeah, we'll be doing some tutorials on deep learning and real bogus and that kind of thing. Right. Okay. So lots of topics coming fast, subject to move around. We're trying to figure out how to, at the same time, introduce the technical stuff. We're trying to introduce a variety of data sets that you'll be using. So don't be surprised if things seem a little mismatched as we're trying to cram a lot of things in. We apologize in advance for that. We're trying to make the most sense as possible. Part of this also is a little on speaker availability. And so again, if it seems like something would fit better on day 2 that ended up on day 3, it's, it's some of that. But again, we're trying to mix and match these technical skills and the data sets that have to do with MMA as best as we can. Right, and so, I highlight a handful of code bases that you'll be interacting with either very, very directly or kind of tangentially. Here, I would say MMA even more so than, let's say, at least variable stars last year, means that you're working with software from the gravitational wave, the gamma ray, the optical, whatever, a variety of these communities, and so these data products that are derived from them. Yeah, so the point here is so we will be providing you some tutorials, some amount of data sets, but there's very little in practice we can do in 5 days. Right, 5 days is not enough, not even close to enough time to even scratch the surface of the, let's say, ongoing research projects that exist within this community. However, we hope that this provides a a small insight and therefore, you know, ideas for, you know, future projects, right? You're like, well, I actually really thought that the, you know, working with the gravitation wave, you know, sky maps or alert projects was really interesting. We can talk about kind of where the field's headed and the kind of things that you might work on when you go home, if that's of interest. There's of course a lot of, you know, a lot to do within the, let's say, light curve modeling of gravitation wave counterparts. Yeah, so, you know, talk to the TAs, talk to me, talk to whoever. You know, we're only going to be able to take you so far here in the couple of days, especially given because the mornings are synchronous and we kind of have those scheduled. The afternoons you can really take in directions that you want, right? You do have, you know, a variety of expertise in a variety of areas, both in this room and on Slack. And so if there are things that you're excited about and interested in, please just ask, because it's a lot. It makes a lot more sense for you to go in the direction that you're interested in than for us to kind of, you know, spoon feed things to you, right? Again, graduate students, you can make these choices. Okay, so in the remaining time, let's talk about ZTF. Right, so we're here at the ZTF summer school. The Zwicky transient facility is a 50 square degree imager on the Palomar 1.2 meter. And this is one piece of what we'll call sort of the ZTF ecosystem that's all on the same mountain. So the idea of ZTF is it has this wide field of view, which means that it can take images of the visible northern sky. Yes, transcription is good. Of the visible northern sky very rapidly. We cover the visible sky every couple of nights or so. ZTF has 3 pass bands, G, R, and I, that aren't too far off from the Pan-STARRS filter set. But on the same mountain, so we have ZTF, which is this transient discovery machine. And on the same mountain, we have the Palomar 60-inch, which houses the spectral energy distribution machine, which is this low resolution spectrograph that runs the that does automated spectral classification of basically all bright ZTF objects. And those spectra and classifications are automatically loaded to TNS, made available for the community. And so these two systems together really are kind of the workhorse of the ZTF system, where ZTF is used to as kind of the transient generator, and then we have the SED machine, which is doing spectral classification. I just want to highlight here something that we at Minnesota are a little excited about. It was like 3-4 weeks ago now, we installed the second version of the spectral energy distribution machine on the Kit Peak 2.1 meter. If you're looking on the slides, you can see on the bottom right, some of you may know, there's a fire that passed through Kit Peak. And so you can kind of see how, let's say the effect it had, got pretty close to the telescope and so on. We haven't been inside, but we have good reason to assume things are okay. But the reason to be excited about this is that the Palomar's 60-inch is something like 1.6 meter. Kit Peak has a 2.1 meter, which means we can go a bit more than half a magnitude deeper to sort of continue the efforts of doing public classifications of these ZTF transients. And so we should get down to, something like 19.5, which as you know, is, not maybe as you know, is not so far from ZTF's limit itself, which is something like 20.5. And so we're not so far away from being able to, do a lot of the ZTF alert stream automatically. And so this, but this is ZTF, but this is a great time to be a graduate student in astronomy, right? We have more and more of these public surveys, ZTF's one example, but of course we have Rubin Observatory, which is an 8-meter class system, that'll see first light in the next couple of years down on Cerro Pachon. And so it'll be doing a reasonably rapid survey of the southern sky. Again, a public alert stream. We have, satellites like TESS that are doing exoplanets, and basically with huge fields of view sitting on different patches of the sky, and doing things like exoplanets and others. But once you get out of the optical, we have gravitational waves, right? So since for the last 7-8 years, we've been finding gravitational waves from compact objects, binary black hole mergers, bineutron star mergers, neutron star black hole mergers, amongst others. And we have IceCube doing high energy neutrinos, and we have examples of multi-messenger sources between neutrinos and other wavelengths, such as with blazars. And so what's cool is most of the some of these surveys have completely public data. Some of the surveys put out kind of alert streams, which allow you to interact with their data, even if the data itself is not public. Most of them put out data publicly after some kind of proprietary period. And so the name of the game in astronomy these days is less and less about, I write a proposal to go to Kitt Peak or to Chile and to go sit at a telescope for a week and take some spectra of some objects. Because more and more, we have these very, very large data sets that, are more or less publicly accessible. And it becomes about, do I have both the scientific and technical know-how with the same data that many other people do to produce interesting science, right? And so it's in some sense, it levels the playing field relative to, some of the past, right? Where, if you didn't have access to a, many meter class telescope somewhere in the world, then you weren't able to do a lot of astronomy. Whereas now across wavelengths and across messengers, if you have the know-how, you can really contribute meaningfully without leaving your room. But to contextualize sort of where time domain is these days, so we have a variety of surveys doing at a variety of cadences and aperture sizes and filters. We've had the dark energy camera on the Blanco telescope down in Chile which ran the dark energy survey for a number of years. We've had SDSS, PTF was the precursor to ZTF, Pan-STARRS, which is on Haleakala, and then, Rubin itself. But what's cool here is that, in multiple hemispheres, down to different limiting magnitudes and in different filters, you have just this amazing variety of data sets that you can use. You can figure out how to correlate. You can do science on all sorts of timescales using exactly the same data set, right? ZTF, last year we were talking about variable stars. Variable stars, right? The objects that you can identify periodic behavior with ZTF, is down to even, minutes now. And then, on the opposite side, ZTF's been running since, around 2018 or so. So, we can, something that's, got a couple year cycle you can find. Similar, it's very similar in kind of let's say the time domain astronomy game. We're studying things like AGN that, have variability on very, very long timescales or, long-lived TDs or whatever. And whereas, we'll look at in this workshop on, GRBs and kilonovae, we've identified many GRBs that last, much less than a night in the ZTF data set. And so the point is, no matter kind of who you are and what your science is, these same data sets are already, contributing to, to what you're doing, right? And so even if you say, Michael, I don't care about multi-messenger stuff. I don't care about kilinovae. I don't care about, gravitational waves, whatever. I say, that's great. These same technical skills that you are putting together while, working on the particular science cases that we're suggesting at the moment. That's the, oh, is that what they do? Okay. So they use VGA. All right. Okay. Potential thing. Okay. All right. Yeah. So you can use the data sets, you can use the skills to apply it to whatever science case that you do care about. And of course, if you're excited about multi-messenger, big thumbs up. We're excited too. Right. And so the the reason that the being able to be comfortable using things like Bayesian inference to do analysis of time series, or use machine learning to be able to classify these objects is, more and more it's becoming hard to get spectroscopy of, a lot of the objects, right? And so, for a long time, the way that, let's say, at least transient time domain science has been done is you take an image, or you take a series of images, identify something that's new, and then you go and take a spectrum of it, right? Look for silicon, identify type 1a supernovae or whatever. And, that's sort of what you were doing. However, with the proliferation of, these time domain survey telescopes, and Rubin, of course, is, the quintessential example of this, it's just not going to work, right? I mean, if you are interested in doing, let's say, fast transient science with Rubin, it would be incredibly challenging to expect to have a functional program which requires, 10-meter class telescopes and a lot of time to be able to do spectroscopic classification of a lot of your fast transient objects. For this reason, the field more and more is moving to, can I functionally use the light curves themselves, a mix of sort of Bayesian methods or machine learning or what have you, to one, identify the subset of objects that I care about, right? I'm working with surveys, so ZTF puts out something like, it peaks out at maybe 1 million alerts per night. Rubin will be, an order of magnitude larger than that, which means that I need to, be able to interact with large data sets. I need to be able to functionally pick out the objects I care about, and I need to be able to apply, methods that will, extract physics from them, right? It's not just like, can I look at an alert stream and can I find something that is anomalous or whatever, but I need methods to be able to say, oh yeah, this is a supernova, or this is a kilonova that's ejecting this this much material and is undergoing our process, and this is the amount. And or maybe I'm interested in doing cosmology, and therefore I need to extract how far away it is and build a sample of them, right? And so this is where the field's headed, right? This is what folks who are getting their PhDs in the next 5-10 years, if you want to be doing a lot of this time domain science, these are the skills you need to be developing. Okay, so if we just look at ZTF itself, this was this is focused on sort of phase 1. Things have evolved a bit since then, but not that much. So in general, right now, something like half of all ZTF data is immediately public in the alert stream, right? So we have a couple of night cadence and GNR bands, and this is the data set that no matter who you are, you have access to. There is proprietary data within the what's called the ZTF partnership, as well as some data that's dedicated to Caltech itself. But what's kind of cool about, I mean, there's a lot of cool things about ZTF, not just sort of this public alert stream, but just share the number of different surveys that have been attempted and are executed on kind of the same system. For example, for a long time, ZTF has been also imaging the galactic plane at relatively high cadence. If I'm someone who wants to do, again, multi-messenger astronomy with future ELISA sources, white dwarf binaries in our galaxy, it is a beautiful data set to be mining. And in some sense, you don't care about, in that case, I don't care so much about the need for immediate access to these. There are these data releases that Avery can tell you all about, where you can go back and, something like we're like 6-month or proprietary period, whatever it is at this point, you can go back and be, mining these public data sets for really interesting objects. The other the other format, right? So we talked about the survey a bit, but a lot of what we'll talk about in this workshop is how do we use ZTF and by proxy other survey systems as a target of opportunity type system. The point is, I get an alert from LIGO or from Fermi or from IceCube or from some other survey that says there's an interesting object in some part of the sky. How do I go about and use ZTF or Rubin or what have you to go and look for potential counterparts? And so this will be a key piece of a lot of the multi-messenger stuff that we talk about over the coming days. And so I kind of hinted at this, or maybe said it explicitly, but ZTF, it functions well as a precursor to what you're going to get with Rubin, right? The number of sources that exists in the databases, some of which you'll have access to this week, kind of number around a billion. Rubin's got more than an order of magnitude more. Again, similar number of detections. There are some ways in which ZTF actually is more challenging than Rubin. The number of annual visits that you'll have in a particular spot on the sky, and so imagine I'm trying to do some kind of time domain science. You need to be able to deal with a lot of observations of the same part of the sky, because Rubin has a smaller field of view and actually more filters. You get just a bit less data. But the broad point is here, like the data with ZTF, it's already big, right? We're talking in the billions of sources, the millions of alerts per night. And if you know how to deal with ZTF, in some sense, it's exactly those same techniques that mean that you know how to deal with the Rubin alert stream. And so for us, I think it is the best proxy and the best preparation that you can have is to feel comfortable working with ZTF data, which means you will inevitably feel, or at least be prepared for working with Rubin data. And so, of course, in some sense, the instrument, the ZTF instrument, the 1.2 meter telescope with the 50 square degree camera, it's just kind of one small part of a much larger observing system, right? So if you go and talk to Avery, you can talk about the processing of the images that goes on at IPAC. You can talk about the archives of not only the images after image differencing is done, but then the photometry that is extracted after image subtraction and the catalogs that are built. And from there, you have these catalog spectrometry, but ingesting those into, terabyte-sized databases where you can rapidly query and visualize these systems. And so this week we'll show some examples of, at least within ZTF and kind of the broader, let's say the broader broker alert ecosystem, how folks are trying to just basically manage the this pipe of data such that you can actually do science with it, right? This is by far the most challenging part at this point. The instruments and sort of the processing pipelines exist, but how do you graduate student, you scientist, go about and extract the data that you need for your particular science? Again, it's both a great opportunity, but incredibly challenging when your colleagues have, access to basically the same data sets that you do, right? How do you analyze that data, quicker, better, faster, more of it, in order to be able to do the science you want, the science you care about? Right, and so we'll give a, so Guy will talk about this on Thursday for sure, but at least the software ecosystem that we've built, which we dubbed Fritz for Franz Wiki, where, again, ZTF is just the input, ZTF data is just the input into a much richer ecosystem of software, of databases and light curve fitting and machine learning and everything like that in order to actually exploit the data that we're talking about. And the great thing about all this, right? All of this code's public, right? So ZTF, we make this huge effort to have open source software that, is unit tested and builds easily in Docker containers online and all this kind of stuff. You'll interact with it some this week. To some extent, as I said, the school itself is a bit of a moving part. I sent out this form probably a little late yesterday, trying to, let's say, reassess in my mind where folks stood and where their interest lied. So please, if you haven't filled out that form yet, some of you have, thank you for doing that. If you haven't done that, please do. It was I posted it in the Slack, so that, figuring out exactly what you're interested in, because some of you may want to go home and build your own, set up the software so you can ingest the data, visualize it, and so on. We have the ability to help you do that here, right? So if this is the kind of stuff that you want to be doing on your own survey, or even just with the ZTF data, but at your home institution, this is all stuff that can happen this week. Okay, so this is, I think this is my last slide for this section. Right? Yeah, okay. So I'm going to kind of end it here, but let's say if I had to give a thesis for the summer school, sort of on a whole, is these days, at least if I focus on, let's say, the study of binary neutron star mergers or something like that, it's at least one example that people think of when they think of multi-messenger astronomy. That one term encodes a lot of different moving parts, right? So if we look at the top left, we have, this sense of astrophysical modeling, but even that entails a lot of different pieces, right? So if I just talk about binary neutron star mergers, I have the solving of Einstein's equations to know what the gravitational waves from, two compact objects looks like. I have the modeling of the radiative transfer that is ongoing in the merger itself, right? So I have this, we'll talk, Shrey will talk more about kilonova, right? But where I have, hot neutron rich ejecta undergoing undergoing our process nucleosynthesis. As the two neutron stars are ripped apart, I have the production of a gamma ray burst and the interactions with the surrounding media. And so I have all sorts of astrophysics, right, just in this one object. Each of those pieces are already, entire research groups, work on those various pieces. We also have instrumentation, right? So we've talked a little bit about ZTF. We've talked a little bit about the SED machine. There's all of these other data sets that you also have access to. And so it really becomes about, how do I put these two things together? How do I take the data sets that are available with the modeling that is ongoing, right? So at least for neutron star mergers, there's papers every day about what do the kilonovae look like, or what are the opacities that exist, in these neutron-rich environments. And you take those data sets and you take that modeling and you put it into, let's say, Bayesian inference frameworks, some of which we'll introduce to you this week, for how do I extract, source properties about the neutron stars based on the optical light curves I have, right? This is a Bayesian inference problem, right? How do I take my alert stream of 1 million ZTF objects per night and I identify the neutron star mergers or the gamma ray bursts or whatever that I care about amongst these objects, right? I'm not just gonna, I'm not in the ZTF era, and for sure not in the Rubin era, just going to be scanning, 1 million objects per night or whatever, in order to try to, by eye, find the objects I care about. Of course, I'm creating, machine learning in other ways to really simplify these searches for me. And of course, at the end, then you can do, after you've done all that, then you can do the science you care about, right? So within my group, we do broadly two things. One, we are interested in cosmology, i.e. measuring the expansion rate of the universe using these kilonovae, which turns out is not a hard science case once you've done all of these other pieces first, right? To do cosmology with kilonovae, in essence, just requires a measurement of distance and a measurement of a redshift. Okay, so there's some subtlety with those two things, but actually relative to all of the previous pieces, that's not so hard. The other cool thing about neutron star mergers is because they're this neutron-rich environment, you can really study the way dense matter interacts, and you can do nuclear physics in the form of measuring, for example, the mass-radius relation of neutron stars. I can learn about what's going on inside of neutron stars, and is there exotic matter and other things. That's a slightly trickier, let's say, a trickier analysis to do, but again, a lot of it is derived from the same framework that you build just to, find them. And again, we'll be introducing you to that framework, or at least the kind that we use Wednesday, I think, something like that. Yeah, so I'm going to say thank you.